Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Dr. Shahid Amin, and in this session of Biosynthesis of Natural Products, Chem 5 to 4, we are going to discuss some construction mechanisms for secondary metabolites. This is first part of lecture 6. So let's see what are the contents of this session. First of all, we'll talk about Wagner-Meerwein rearrangements, followed by Aldol and Claisen reactions, and imine formation along with Mannich reactions. The reference book we are following, this is Medicine and Natural Products, a biosynthetic approach by Paul M. Doig, and this is third edition from 2009. So first we'll look at Wagner-Meerwein rearrangements. During the biosynthesis of different natural products like terpenoids and steroids, some specific type of 5-carbon units that we discussed before that are named as isoprene units, these are utilized. Sometimes these are utilized as such, but many times they undergo a process of rearrangement, where one part of the molecule it rearranges, that is, the shifting of groups may occur. So this happens by this specific process that we call as Wagner-Meerwein rearrangement. So these rearrangements involve carbocation intermediates. Carbocations are positively charged ions that have positive charge over carbon atoms inside the ion. Here we can see some carbocations like this one as a whole. This is a carbocation because it contains a positive charge over one carbon. This is another carbocation that has been formed as a result of transformation. And here another carbocation, another one, and some other carbocation shown here. Now, when these rearrangements happen, there are different types of shifts, that is 1,2 shift, 1,3, or longer shifts. And these shifts may be that of hydride, methyl, or some higher alkyl group. If you look at this example, the first one, here we have this species that has a positive charge over this carbon. We may regard this carbon as carbon number 1, and the second carbon, this is carbon number 2. The hydrogen that is attached to carbon number 2, it may shift towards carbon number 1, along with both of the electrons that are making covalent bond between this carbon and this hydrogen. So when this hydrogen will be coming to this carbon along with 2 electrons, this hydrogen will be known as a hydride, because hydride is a negatively charged hydrogen ion. So it's shifted here. As a result, this carbon will become now 1 electron deficient, so it will now acquire a positive charge. Similarly, here, this is a methyl group, this is CH3. If it's transferred from here along with both of the shared electrons towards this carbon, so this carbon will ultimately get a positive charge. So one carbocation will be converted to another one. Similarly, here, this group, that is the alkyl group, it will be transferred to this carbon, and this carbon ultimately will have a positive charge with the transformation of this structure. Similarly here, this hydrogen is transferred from here to this carbon, so this is another type of shift. So if you look at the positions of these shifts, for example, here it's being shifted from 1, 2, from 2 to 1. So this is known as 1,2 shift. And because hydride ion is involved, so this is 1,2 hydride shift. Here, a methyl group is involved in a similar sort of shift, so this will be known as 1,2 methyl shift. Here, this is an alkyl group, so this will be known as 1,2 alkyl shift. In this in case of this species, this shift is 1, 2, 3. This is 1,3 shift. So, and hydrogen is involved, so 1,3 hydride shift. As a result, when this carbocation is produced, it has a conjugated structure. So the reshuffling of electrons, that is another type of, we don't say this is a rearrangement, rather this is a resonance of electron cloud. So this electron cloud will move here, and as a result, we will be having another carbocation. So both of these 2 carbocations, these are the resonance contributing structures towards overall carbocation. Similarly, if you look at this structure, here is happening 1,2 hydride shift, As a result, a positive charge will happen here. Then this hydrogen that is attached to further position number 2 as compared to this position, so it will be shifted from here. Then further this method will be shifted here, then this method will be shifted here. So this is a long range shift that is involving hydride as well as methyl groups. So this is, but all of these shifts, these are 1,2 shifts, whether it be 1,2 hydride or 1,2 methyl shift. All of these shifts are known as Wagner-Meerwein rearrangements. Now, there is question why these rearrangements happen. What's the reason that this type of transformations happen? So, their reason there may be that they are going to work. These rearrangements happen for generating more stable carbocations. We know carbocations may be primary, secondary, tertiary, and out of these three, tertiary carbocation, these are the most stable one, followed by secondary and then primary. And at the end, there is methyl carbocation, that is a carbocation that is derived from simple methyl group. The second reason may be the a relaxation of the ring system, the ring strain. If there is, for example, there is a smaller ring, there will be much more ring strain. The energy of the molecule will be very high. So as a result of transformation, for example, a 4-member ring may be converted to 5-member ring. As a result, the ring strain will be decreased and achieving high stability for the molecule. So this is a favorable process. For example, if you look at this example, this carbocation is a secondary carbocation because the carbon that is attached, that is having a positive charge, this is further attached to 2 carbon atoms that are part of this alkyl group as well as this alkyl group. So this is a secondary carbocation. When this hydride shift happens, it's converted to a tertiary carbocation because now the carbon that is having positive charge, this is attached further to 1, 2, and 3. 3 carbon atoms, so this is a tertiary carbocation. And we know that tertiary carbocation is more stable as compared to secondary one, so that's the reason behind this transformation. Similarly here, the case is similar to this one. The only difference is here was hydride involved, but here is a methyl involved. So secondary carbocation is being converted to a tertiary one. In case of this structure, here we have a tertiary carbocation. It's transformed to a secondary one. The reason here being that in this structure, although the carbocation is tertiary, but this structure contains a 4-member ring. 4-member ring has a very high ring strain. So when it converts to this structure, now it's being transformed to a 5-member ring. 5-member ring has far more less ring strain as compared to a structure containing 4-member ring. So achieving stability. Now, stability may be achieved by converting more stable carbocation or producing a system that has less ring strain. Now, this is the case of simple organic reactions. In case of biochemical reactions that are enzyme mediated, carbocations as such, like discrete species like these are shown here, these may not exist during these transformations. So what's the actual case? The electron density, we talk about the loss of electron density or the decrease of electron density. So if the electron density is decreased too much over one carbon, that will be regarded as a carbocation. Now the second type of transformation, this is Aldol and Claisen reactions. Aldol and Claisen reactions both achieve carbon-carbon bond formation. And normally these are base catalyzed reactions. And during these reactions, for example, if you talk about Aldol condensation or even Claisen reaction, enolate ions that are resonance stabilized, these are produced. And the starting material that is used in both of these reactions, these are the carbonyl systems that may be aldehydes or ketones. Suppose here we are having this keto group, and this is a ketonic or aldehydic species. This X may be hydrogen, it may be an alkyl group. So this carbonyl group is highly polar because of high electron activity, large electron activity difference between carbon and oxygen. As a result, oxygen is partially negative and carbon is partially positive. This partial positive charge over carbon induces partial polarity in these bonds that are bound between carbon and hydrogen, that is over this carbon. So these hydrogens also attain partial positive charge. So these are somewhat acidic. So if we use a strong base, that strong base may attack to this carbon. As a result, this electron pair will be shifted towards oxygen. But if it attacks this hydrogen, that is acidic hydrogen, then this electron pair will be shifted here, and this electron pair will be shifted to oxygen, getting a negative charge over oxygen. So overall process will give us with this species. This species contains carbon-carbon double bond. So this is ene system, and it contains O. If there is one H also, it will be alcohol. So this is ene alcohol or enol. Now this alcohol has lost the proton, as it seems. It has acquired a negative charge, so it will be named as enolate ion. So this is enolate ion. This enolate ion has a conjugated system, like this is double bond, single bond, and negative charge. So this is a resonance stabilized structure. So these are two resonance contributing structures for this enolate ion. Similarly, another one example, in case when enzymes that are biochemical reactions are concerned, then the enzymes that have some groups that can give off electrons as electron pairs, or and these are present as lone pairs of electrons. So they will be acting as a base, and or for example with this species, and they will be generating structures like, if for example they attack this hydrogen, this electron pair shifts here and this electron pair shifts here, carbon dioxide will be released and an enolate ion will be produced, but not directly as enolate ion, rather it will be as carb anion, that is a negative charge over carbon atom. Then this electron cloud may shift here and this oxygen may shift here, so as a result we will get an other enolate ion. Whether we talk about an Aldol type or Claisen type reaction, that which type of reaction will be happening, which type of product will be formed, it depends upon the nature of X, that is the group attached to a carbonyl group, and then its potential of this group X as a leaving group in the alkoxide anion intermediate. The alkoxide anion that we previously seen, that is an enolate ion. Suppose we have this enolate. This is not in the form of enolate, rather in the form of a carb anion. This is generated, and this is another molecule, aldehydic or ketonic molecule. This negatively charged carbon will attack this carbon that is partially positive, and this electron pair will be shifted towards oxygen. As a result, we will get this intermediate, that is alkoxide ion. Now this alkoxide ion is an intermediate. This electron pair, if it moves here, so this X will be leaving. If this X is a very good leaving group, this reaction will be very easy. As a result, we will get a structure like this. But if it cannot leave as a leaving group, that is, it's not a good leaving group, then this species will acquire one proton from the medium. As a result, it will be converted to a structure that contains an OH group along with a keto group. If this keto group is, for example, it has H here, it will also be definitely H. So because these are two similar, these are derived from similar species. So in this case, this is aldehyde, and this will be alcohol. This will be known as aldehyde alcohol or aldol. But here, if this group acts as a leaving group, then we will get a product that is a diketonic product. This diketonic type of product is named a Claisen type product. This is Claisen reaction. But this one, this is aldol reaction or aldol coupling, and this product is known as an aldol. Thus, chemically, two molecules of acetaldehyde, for example, if we are using here, they yield aldol because hydrogen is not a good leaving group, while two molecules of ethyl acetate, if we utilize these, they will give us acetoacetate, because in that ethyl acetate is a very good leaving group, so it will leave and we will get this type of product. Now these processes are vitally important in the biosynthesis of both secondary and primary metabolites. But when there are enzyme catalyzed reactions, they don't need strong bases. So the groups that are present as part of enzymes and that are basic groups, they will act in order to bring about these reactions. Nevertheless, the reactions do appear to parallel enolate in ion chemistry and are frequently responsible for joining together C2 acetate groups because of these reactions. In most cases, the biological reactions involve coenzyme A esters, for example, acetyl coenzyme A, that is the thioester of acetic acid. So this is structure of coenzyme A. It has specific parts. For example, if you start from right side, this is adenine nitrogenous base, then it has 5 carbon sugar, that is ribose, along with 2 phosphate groups. So this part is known as ADP, that is adenine plus ribose is known as adenosine, and this is diphosphate. So adenosine diphosphate, along with that is attached pantothenic acid part, this one, and then there is cysteamine part. So this is here. So collectively, this is known as pentothene, and overall this molecule is named as coenzyme A. So if it accepts an acetyl group that will be attached to this sulfur, it will be named as acetyl coenzyme A. Now, this thioester has significant advantages over oxygen esters like ethyl acetate that we have talked about before during a discussion of Claisen type of reactions. There are 2 reasons. The first reason is that alpha methylene hydrogen atoms are more acidic comparable in fact to those in the equivalent ketone because of electron delocalization in an ester group because of the oxygen atom, and this increases the likelihood of generating an enolate anion. Like if we have for example this one ester, it generates this enolate type of anion, but in case of this thioester, this hydrogen will be more acidic because there is no chance of this type of resonance, because there is sulfur atom at a sulfur size is much more bigger as compared to oxygen. So the transformation of this type of transformation, although sulfur has lone pair of electron, but this type of transformation not that much easy in case of sulfur containing molecules. If we have this one, so this type of transformation, this is less favorable. The second reason is that thioester has a much more favorable leaving group than the oxygen ester. So this group that is named as ethoxide, it's not good leaving group as compared to S coenzyme A. That is a much more favorable group as a living group. So when this reaction will happen, for example, this alkoxide ion will be generated during the Claisen reaction, then this transformation is much more easier. That is, this electron pair will move towards carbon, and as a result we will be having a double bond, and sulfur containing group, it will be lost. So, but in this case, this is not so much favorable. Now, when these two effects combine, they increase the reactivity for both Aldol and Claisen type reactions for the molecule that contain S coenzyme A. Thiester linkage also provides a means of covalent bonding, suitable substrates to enzymes because of the presence of this sulfur. So attachment to the enzyme becomes very much easier. And then afterwards, the further reaction is also facilitated. Like if, for example, we have this type of group that is part of enzyme, it may carry out this transformation very much easily, and then afterwards, when the reaction is complete, for example, first this group has attached to the enzyme, part of the enzyme containing the sulfur, and afterwards this nucleophile, that is the second species that has to react with this molecule, it will attack this carbon, and as a result we will be having a product, and the enzyme will be leaving as such. Claisen reaction is involving Claisen reactions that involve acetyl coenzyme A. These are made much more favorable by first converting acetyl coenzyme A into malonyl coenzyme A by a carboxylation reaction catalyzed by three-component enzyme acetyl coenzyme A carboxylase. This reaction involves carbon dioxide as a carboxylating agent, ATP as a source of energy, and coenzyme biotin. The conversion of acetyl coenzyme A into malonyl coenzyme A means that alpha hydrogen atoms are now flanked by two carbonyl groups. As a result, the acidity of the hydrogen that are attached to that are between two carbonyl groups, it will be increased too much. So it will be much easier to deprotonate such a type of species and generate for generating the carbon anions. Thus, a more favorable nucleophile is provided for the Claisen reaction. The carboxyl group introduced into malonyl coenzyme A is simultaneously lost by a decarboxylation reaction during the Claisen condensation. So it's shown here. For example, first of all, we have to convert. We have to get the activation of our group, and this activation is brought about first converting this bicarbonate, that is actually the aqueous form of carbon dioxide in the form of bicarbonate ion, utilizing ATP in the presence of this enzyme biotin carboxylase. It will be converted to ADP, and this mixed anhydride will be generated by reaction of this bicarbonate with ATP. Then biotin enzyme will act on the species and getting this carboxyl group, and this carboxyl once this group gets attached to this biotin enzyme complex, then the carbon ion that is derived from acetyl coenzyme A, it can very easily react with this form of carbon dioxide, actually activated form of carbon dioxide that is bound to the enzyme, and this reaction happens for converting that carbon dioxide into malonyl coenzyme A utilizing acetyl coenzyme A. So this carbon dioxide in the form of bicarbonate now has become part of this malonyl coenzyme A. Malonyl coenzyme A is far more good species for these reactions, for aldol or Claisen reactions, as compared to simple acetyl coenzyme A. So this is sort of fixation of carbon dioxide, and this fixation by this biotin enzyme complex is not unique to acetyl coenzyme A. Other important examples that occur the similar way, there is, for example, oxaloacetate that is generated from pyruvate in the biosynthesis of glucose from non-carbohydrate sources. We have a process that is named as a gluconeogenesis. This process is we have this malonyl coenzyme A, and malonyl coenzyme A will, as we discussed, that this is activated. So these two hydrogen that are here, one of the hydrogen will be detached as a proton, and this will this can attack, the electron density can attack this carbon that is partially positive, and because of loss of one proton from here, carbon dioxide will be released, and this carbon will get attached to this carbon, and we will get this kind of species. Afterwards, rearrangement will happen, of electronic cloud, as a result of which this electronic cloud will be shifted here, generating a carbonyl bond, and this group as coenzyme ASH, it will be released. So we will get acetyl coenzyme A as the product. Now we talk about the reverse Aldol and reverse Claisen reactions. These are actually, they also these are encountered during the biosynthesis or modification of natural products. These reactions remove fragments from the basic skeleton that is already generated, but once these reactions happen, they will transform one type of secondary metabolite to some other one by detaching a small part from the structure of that secondary metabolite. The reverse Claisen reaction is a prominent feature of beta oxidation sequence for the metabolic degradation of fatty acids. That is a two-carbon process where two carbon units as acetyl coenzyme A. These are cleaved off. These are released from the main chain of fatty acids, and this way the fatty acid chain reduces every time by 2 carbons, and the chain length is shortened. The process simply could be shown this is fatty acetyl of a fatty acid group that is attached to coenzyme A. So this is acyl coenzyme A. This acyl coenzyme A will be acted upon by enzyme acetyl coenzyme A dehydrogenase. Hydrogen will be released, and a double bond will be generated here. Afterwards, hydrolysis will happen in the presence of inoyl coenzyme A hydratase enzyme, and because of this hydrolysis, we will get this type of alcohol. And this alcohol later on, it will be reduced in order to produce a carbonyl group here, and one hydrogen, this one, and this hydrogen, these are removed, and we have a diketo group, a dicarbonyl compound here that will be further acted upon by enzyme sialase, and it will be finally converted to acetyl coenzyme A and another acyl coenzyme A, but this acyl coenzyme A is 2 carbons less than the original acyl coenzyme A. So these 2 carbons are released in the form of acetyl coenzyme A. Now we talk about imine formation. What's imine formation? Actually, in this reaction, carbon-nitrogen bond formation happens, and this is frequently achieved by condensation reaction, that is nucleophilic addition followed by dehydration between an amine and an aldehyde or ketone. The product that is formed as a result, this is known as imine, or more general name for these products is Schiff's basis. Reaction happens like this is electron donor, this is electron deficient carbon. So this is acting as a nucleophile. This will attack this carbon. This electronic load will be shifted towards oxygen, and we will be having a species like this. Afterwards, if proton is released from here, we will be having a species like this, and that will be ultimately converted to this kind of product. If this is a the starting material we have used, this is an aldehyde, but if we use ketone, a structure like this one will be produced. Similarly, if we use a secondary amine will produce a structure like this one. This difference being that there will be a positive charge over nitrogen in case of the reaction of secondary amine with aldehyde or ketones, but with primary there is no positive charge over nitrogen. So here this imine will not be as a free imine, rather this will be in the form of a salt that is known as iminium salts. The imine that is produced as a result of these reactions in its protonated form, like this one is, although this is not protonated form, if for example we are having this structure and it loses its lone, it donates its lone pair to one proton, it will get a positive charge. But that protonated form of this Schiff's base, this can react as this can act as an electrophile in the further reactions like Mannich reactions. So if we talk about the reverse of imine formation, that is the hydrolysis of imine formation, hydrolysis of imine, it will give us the original starting material that are aldehyde and ketones. This is also an important reaction in the synthesis of secondary and primary metabolites. This reaction could be shown very easily, like this way: that proton, that oxygen of water containing lone pairs of electrons, it will be attacking this carbon that is again partially positive, and this electron will be shifted towards nitrogen, and one proton will be accepted. The result ultimately will be having an amine and a protonated form of the carbonyl compound that later on can lose proton in order to be converted to original ketone or aldehyde. Now, Mannich reaction is encountered through alkali biosynthesis, and its most general form involves combination of an amine and aldehyde or ketone, as we have seen in the previous slide, for the formation of Schiff's base. So that amine that is produced, it will then further react with the molecule that contains a nucleophilic carbon. So if we look at this structure, this is a protonated form of imine, that is iminium cation. If it's reacted with a carb-anion type of species, that is a nucleophilic center, it will attack this electrophilic center, and we will get structure like this. This product is a product of the Mannich reaction. This reaction is Mannich reaction. The nucleophile might be provided by an enolate ion, anion, or in many examples by a suitably activated center in an aromatic ring system. Just as two carbonyl compounds can react via an Aldol reaction, so can two imine systems. Like if you have, suppose this is an imine, it gets protonated, and these are two forms of this protonated form of imine, just like the enolate ion. If this protonated form of imine, it reacts with non-protonated form of this the other form of this protonated form of imine, that is other resonance transformed structure, it will, the product formed will be like this, and it happens because of this transfer of this lone pair of electron towards this carbon, and this electron pair will be attacking as a nucleophile upon this partially positive carbon. This electronic load will be shifted towards nitrogen and will get a species like this. And this reaction is just like aldol condensation reaction or aldol type reaction. Often aldehyde ketone substrate in enzymatic reactions become covalently bound to an amino group in the enzyme through imine linkages. In so doing, they lose none of the carbonyl activation as a consequence of the new form of bonding.